Thank you for the invitation to come and speak about this material. So yeah, so I want to use today's talk as maybe a way of introducing some kind of derived category methods, which are useful in understanding the this theory of coherent singular support that is going to be the subject of these 3 talks. So we probably won't really get to it today, but we'll make I think, very good headway. So I want to say this theory is a little bit abstract at times, but I want to start with something really abstract, which of course is the worst way to start a math talk, but bear with me. So I want to start with a little bit of an overview of mathematical research. So the place to really start with something like that is that first you have to want something. So you go to your friend and you say, I really want this thing to be true, or you have some kind of idea, some dream, and well, then you step 2, you really kind of calculate something. And unless you're one of the very fortunate few of mathematicians for whom everything goes perfectly, what you realize here is that you made a mistake in what you wanted. It wasn't quite accurate, and so the last thing you do is you kind of salvage what you can. And this is really kind of this whole step is where technical things happen. So, you say, oh, except in these cases, and I'm not even really sure if these cases don't exist or do exist or whatever. Or you might, say, oh, well, predicated on the Riemann hypothesis, I can show, or whatever kind of thing you do. But this is where math typically gets technical. And then there's kind of an optional, maybe 4th step, which is that you then tell people about the pitfalls that you ran into here, and you could develop some kind of more elaborate theory. So, various examples of this whole pattern would be, just when you're starting off in the very beginning of math, you think, oh, I can integrate functions. But you realize, no, you can only really integrate volume forms. And so you develop a whole theory of differential forms and this kind of stuff to account for where you went wrong. Yeah, and so the subject of this coherent singular support is really about this technical stuff. Like it's telling your friends where certain pitfalls are, and yeah. So I want to really start, as much as possible to kind of begin in this place 1. By the way, I also wanted to say this exact pattern works really well for maybe this sort of narrative structure works well for Broadway plays or something like this too, right? So you start off, you want something, there's a struggle, and then at the end you don't really get what you wanted, but you sort of get what you deserved. Okay, so I just want to, so I'm going to kind of introduce notation as I go along. So K always it's going to be a field of characteristic 0. So characteristic 0 won't really be relevant for a while, but I don't want to introduce it at the last possible second, so it'll just be, from now on, it's field of characteristic 0. Not relevant at all for what I'm saying now. So I'm going to take K of epsilon, and I've learned that I always mean, so for me, epsilon always squares to 0. So if I write K of epsilon, I just mean K of epsilon mod epsilon squared. So if you take, so what I want to recall is that there's an equivalence between flat K of epsilon modules and the following kinds of data. So self-extensions of a vector space. So V is a vector space over K. So these flat modules over the dual numbers are the same as a vector space plus a self-extension. Let me just very briefly remind the construction. So first of all, if you have, so given this kind of short exact sequence, you get a k of epsilon module E, where, yeah, now it's bad notation, epsilon from E to E is given as follows. So first you project onto V, and then you include into E. And that clearly squares to 0, so it really gives you a k of epsilon module. And it's easy to see that it's flat. And to go the other way, if you actually have a flat k of epsilon module, so maybe M is a flat k of epsilon module, then you take your V to be M mod epsilon, and your self-extension will be that the map of multiplication by epsilon factors through M mod epsilon, and in the case where M is flat, this is really an injection. So this maps onto our V, which again was M mod epsilon. So this is a very convenient perspective on modules over dual numbers. So you use this in computing tangent spaces of Picard varieties and such things kind of all the time. So as a very erudite student of derived categories, you look at this and you say, I know how to make this more general. What I should do is remove the word flat and then work with derived categories downstairs. So this is what you what it tells you on page 1 of your derived categories textbook is remove the word flat or remove the word projective or remove the word injective and work with derived categories, and you should be working very well. You should get true statements and so forth. So the kind of guess here, or let me put it better. The hope, the want, is to have the following. So that k of epsilon modules. So I'm going to, for convenience, use this to mean sort of suitable derived category. So I don't mean the abelian category. I mean the whole derived thing. That this would be equivalent to a suitable derived category of vector spaces. Again, I'm using the notation in the same way. So just for convenience, essentially everything will be derived. And so if something's not derived, I'll make that very clear. So V, a vector space plus a self map from V to V with its shift by 1. So that's the kind of thing an extension would usually cover. OK, so as hinted above, so this is wrong, and for somewhat subtle reasons. So in order to explain these subtle reasons, I have to give a little bit of a digression about how to do calculations of this kind. So what we're going to find is that it's possible to essentially make a mistake and think that you proved this theorem. And so we have to be very careful about how we proceed in this stuff to make sure that we actually prove our theorems correctly. So here's some kind of general yoga on derived categories. So I'm going to start with C being some DG category. So let me just say very briefly what I mean by this. So at first approximation, what I mean is this is a category which is enriched over chain complexes. However, I really want to think about C as an object of the infinity category of DG categories. And what that means is that for all sort of practical purposes, I can't distinguish a quasi-isomorphism from an isomorphism between chain complexes. So that's what working at an infinity categorical level gives you. And so it tells you, if you take what I said very literally, a category enriched over chain complexes, when you say chain complexes, you can distinguish them, even when you have a quasi-isomorphism between them. It might not be an isomorphism. For me, I'm not allowing myself that luxury. So OK. So that's the first thing. So C is the DG category, and DG stands for differential graded. So that's just a kind of short thing for chain complexes. And I'm going to assume that C has all homotopy colimits. And this is equivalent to having all infinite direct sums. So it's not such a fancy condition. So now an object, so definition, an object f in C is compact if, so the functor that takes the chain complex of maps out of F from C to vect commutes with colimits, or equivalently, all direct sums. So this is a smallness condition on an object. So usually if you just think in terms of abelian categories, a module will satisfy the corresponding property that Homs out of it commute with all colimits if it's a finitely generated projective module. So this is some kind of generalization of that. Great question. It's because of my convention from over here that everything is derived, so vect means chain complexes. Yeah. Other questions? Yeah, so when I say commutes with colimits, one example of a colimit in this world is a cone. And so if you work at the level of actual vector spaces, like non-derived, you'll get long exact sequences instead of, whereas what I'm like this functor isn't going to send cones to co-kernels. It'll send cones to, I mean, if you take cohomology. OK, sorry. So maybe confusing thing to say. Vect here means the derived category, or the DG category properly. So now, so let me just kind of give very quickly an example. So if A is a ring of whatever kind, then the object A inside of A mod is compact. So roughly what this is telling you, so what does Hom out of A do? In this case, well, it just forgets that you are an A module, a complex of A modules here, and thinks about the underlying vector space. And that's saying that essentially that functor commutes with direct sums is saying, for instance, that if you kind of take a direct sum of A modules, that's again an A module, that commutation. So here, ring, I could really mean a DG algebra over K. I want to work in a suitable derived setting. And then there's a kind of converse to this principle. So again, definition is that F is, maybe I'll give a couple of definitions first. So I'm going to say C is compactly generated if, so roughly what the definition says is if there exist enough compact objects. So if F in C is 0, so this is a condition. Let me say this better. If Hom in C from G to F equals 0 for every G in C compact, this implies that F is equal to 0. So in other words, every object which is non-zero should receive a non-zero map from some compact object. So that's what I mean by there being enough compact objects. So the first thing is that in this case, if you take the subcategory of compact objects, so CPT for me means compact. Then you can recover C canonically. So here this is one of the places where it's important to work with higher categorical methods or some substitute. So the kind of statement I'm saying doesn't work otherwise. So namely, C is going to be what's called the ind category of C. So in Ben's talk, he explained that suitably understood simplicial commutative rings, for instance, can be recovered by sort of formally adjoining certain colimits to certain kind of smaller categories, let's say, of usual rings. So here you do something similar. So you take this category of compact objects. It's not going to have all direct sums by any means, but if you freely adjoin all direct sums, then you'll recover C from this smaller category. So again, a kind of example, just to have in mind, is that if you take this category of A modules again, this is going to be what's called perfect A modules. So these are a complex of modules is perfect. So perf of A is the smallest subcategory of A mod, containing A enclosed under shifts so cones, or I could put finite colimits and sum ends, so direct sum ends. Yes? What was that?
Why these things won't work in standard direct category?
The only thing that won't work is the passage to the int category. So I kind of gave it a universal property, but that only makes sense essentially in the infinity category of DG categories, the way I said it. OK, other questions? OK, so now I want to add to these definitions just a little bit more. So definition. So a compact object in C is a compact generator. So first of all, it should be compact. OK, maybe I'll say it this way. It is a compact generator if F is compact. And OK, the order will go the other direction now. So if it by itself, without the assistance of any other compact objects, can tell whether some object is 0. So if whenever Hom from F to G is 0, this implies that G is equal to 0. So this is another example. So A in A mod is a compact generator. So this is essentially the principle of working with derived categories. So if you work with a derived category of modules, an object is 0 if it's sort of 0 as if its underlying complex of vector spaces is quasi-isomorphic to 0. Now there's a converse to this. So conversely, if F and C is a compact generator, then you end up with an equivalence as follows. So we'll get C is equivalent to A mod, where A is going to be the algebra of the DG algebra of endomorphisms of my object F. And the functor sends, so the functor here is Hom out of F. What did you say? So in the I put in an assumption in the beginning that C has arbitrary direct sums. Yeah, so it's actually forced on you by a version of the adjoint functor theorem that if you have all colimits and some set theoretic conditions aren't horrible, then you also have all limits. So abstract category theory covers your objection. So this now is our very convenient strategy. So so let me sort of reformulate our problem. Our hope. So what we had was k of epsilon mod was supposed to be equivalent to something. And it's gone now, but let me just remind you, it was vector spaces with an endomorphism of degree 1. So it shifted the complex by 1. And if you think about what that is, I didn't maybe come up with a good, OK, I'll say the following. So B is going to be the tensor algebra. So this is the free associative algebra on k of minus 1, or free DG algebra on k of minus 1. So when I say DG algebra, I'll be careful if I mean commutative. Here, I'm not requiring commutative. So just for a sense for how this algebra looks, its cohomology is in positive degrees, and it's one-dimensional in each degree. So it's a tensor, like the tensor algebra in the derived world looks just like in the usual world. It's a direct sum of tensor powers of your module. So here so what I want, our hope was that this category of modules over the dual numbers was equivalent to B mod. That's another description of the category I wrote down, because it's easy to describe modules over a tensor algebra. So now we have a very good strategy. What we should do is find a compact generator inside of k of epsilon mod and try to show that its endomorphisms are equivalent to B, RB, so to speak. So, OK, well, what can we do? So of course, if we're looking for a compact generator, the first place to look is k of epsilon. But that just gives us the sort of, that identifies k of epsilon mod with itself. Nothing interesting happened. So if you look really at what our construction for flat modules was, what you try is to take sort of F, our compact generator, to be k. So here, epsilon x by 0. as it must. So this is k of epsilon mod. So a quick calculation shows that indeed, if you take this complex of endomorphisms of k as a module over these dual numbers, that this actually is equal to our algebra B, which is a great start. So let me just kind of comment on how you would prove something like this. So you have the favorite resolution. So you have this favorite resolution of k. So here, all of my complex in every degree less than or equal to 0 is just k of epsilon itself, and all of my differentials are multiplication by epsilon, and they square to 0 because epsilon squares to 0. So we have this favorite resolution, and you can use this to compute the self-x of this object, and you'll find that they're one-dimensional in each degree. In particular, because this is a free algebra, that generator in degree 1 will give you a map from B to this algebra. And then it's just some, so once you actually have a map of DG algebras, it's just, you need to check that it does the right thing on cohomology groups to see that it's actually an isomorphism of DG algebras, and meaning quasi-isomorphism. And so that's a simple calculation, again, using this resolution. So I'll just, I don't want to get sucked too into the details of it, but that's how you do that. And if you want to talk out details, we can do that after the talk. So that's most of the way there, except that there's one problem, which is that k is not compact in k of epsilon mod. So let me just kind of very briefly prove that. So the idea is that you use this same resolution. So you define Fn to be the complex, let's say, k of epsilon. This will be degree minus n. This will be my epsilon. Mapping to, so down here are the cohomological degrees. So so in other words, you just do this stupid truncation to my favorite resolution. What you'll have is that k is equal to the direct limit over n of these objects Fn. But if k were compact, it would be a summand. Of some Fn, and you can see that that would contradict the calculation about self-x. So contradicts the self-x calculation. Another way to say essentially the same thing is you could say that every perfect complex has the property that x out of it will vanish in sufficiently high degrees if you map into k. So that's a statement you could just prove by induction in this description of perfect complexes that I said. And again, it would, applying that to, well, there would be a contradiction with the infinitely many self-x. So our yoga doesn't apply in this case, which is too bad. There are various ways that we can correct this. So that kind of covers step 2 of the algorithm for research. So we did our calculation, and we realized that we were wrong. So we tried a very good strategy for proving this equivalence, and it failed. The module wasn't compact. And now what we want to do is we want to make things more technical in order to get true statements out. And so one way to correct this is that I'm going to define what's called co of k of epsilon. So this is a subcategory of k of epsilon mod to be the full subcategory of bounded complexes with let's say, finite dimensional cohomology. So this is a larger category than perf of k of epsilon mod because it contains k, whereas perf of k of epsilon did not. But clearly, any perfect complex does satisfy this property. So now, if we take category ind of co of epsilon, so this should be read as ind of co k of epsilon, then we do obtain, well, what we end up with is an equivalence with B mod. Because what I claim is that k is actually, OK, I see some confused faces. So what I did was I essentially rigged my setup so that this would be true. So here, k is an objective co, just by fiat. So it satisfies that property. And I claim it actually generates. That's just essentially that's because if you take something like k of epsilon, it's a self-extension of k by itself. So it's actually a generator. So the proof here is that k generates, k is compact in ind of co of k of epsilon. Sorry, I forgot. I can just write ind co. It is compact by fiat. It generates. And its endomorphisms are the same. So endomorphisms of k in here are exactly B. Sorry, let me put it this way. So endomorphisms of k in this category co are going to be the same as endomorphisms in k of epsilon modules, because co is a full subcategory of both this ind co and k of epsilon mod. And therefore, endomorphisms are the correct thing. Maybe I can pause for questions for a second. Yeah. By fiat, it means that I was the dictator of this setting, and I said that it must be in this way. Yeah. Other questions? No, but I mean, in this context, what it means is when I write ind of some category, it means everything is compact in that ind category. It was a kind of, yeah. Didn't exactly formally say that when we did the ind categories. Other questions? Yeah. OK, so let me say the next thing, and then I'll return to your question. So let's pause for a second. Yeah. So perfect modules over k of epsilon are contained inside of coherent modules over k of epsilon. And this gives me a fully faithful functor. From k of epsilon mod. So by so when I apply ind, on applying ind, you get a fully faithful functor from k of epsilon mod into this ind co of k of epsilon. OK, so now we said that this was equivalent to this category of B modules using Hom out of K. By the way, I kind of meant to give as an exercise. Let me pause for a second. So an exercise would be to check that this functor I wrote down to B modules actually corresponds to what we did in the very beginning of the lecture. So that's just a kind of good thing to work through, I think. So now the question is, which subcategory do I get in this way? So claim is that k of epsilon mod corresponds to the full subcategory of G inside of B mod, where, so I'll call this B mod locally nilpotent. So the full subcategory consisting of objects where if you take the, if you take the direct limit of the diagram G maps to G shifted by 1, so let's remember what B modules are. They're exactly just vector spaces equipped with a map like this. And then you can iterate this map. And what I ask is that this colimit be 0. So let me just briefly kind of sketch the proof. So if you consider where k of epsilon itself maps under this functor, it maps to k. And the map k to k shifted by 1 is 0. What this map encodes is the self-extension k of epsilon of k by k. It's clearly split. So this map is 0, and therefore, this condition here is closed under colimits. So if I take a colimit of objects in this subcategory, I get another object of this subcategory. And so therefore, like the way the functor I just said was constructed, this category is closed in here under colimits. So I get an inclusion in one direction. To go the other way, all you do is you say, what you need to do is show that k is a compact generator of this category, the image of k of epsilon here. And that's, let me leave that as another exercise. You should really use this local nilpotency in a smart way. Let me just leave it there. OK. Back to Piotr's question. Do you want to ask it again? So it's what happens when you apply Hom to it?
Yes, I mean that showed that the k was not compact. But now you change your category, but somehow the fn's are still in your category, so the colimit is in your int.
Yes. But so what happens is that OK. So I guess there are kind of two questions there. So the first one, let me just, in case it helps. So the first one doesn't exactly parse. So the one about what objects are there in k of epsilon mod that aren't in int co. It doesn't parse in the sense that k of epsilon mod embeds fully faithfully into here. So this INTCO is a bigger category than the sort of naive category of modules. Next, there's 2 copies of k. So this is a confusing thing. There are 2 copies of k inside of INTCO, the trivial module. One of them is the copy that lives inside of co, and that's the compact generator I just chose. That object is compact. The other one is the object you just talked about. So I could take this resolution if you want. What that does is realize k sort of explicitly as an object of k of epsilon mod, or end of perf if you want. And then I could take the direct limit in here. And that's going to be a different copy of k. So that my k is not in the image of this functor. And so the one you just said is not compact in here either, but mine is compact. So. What's the top line and then mapping perf into k mod? So those are the same functor, yeah. So by what? By fiat again. Yeah, so this arrow is doing a lot of work. So this arrow says that this gives rise to this fully faithful functor. So what you do is you say, here I have perf of k of epsilon mod. Sorry. Yeah, perf of k of epsilon. If you go all the way here, it maps to k. When you run this functor, this equivalence between here and here, OK, so there's 2 things going on. So one of them is this kind of specific causal duality kind of thing that's going on. And so let's forget about that for a second. Then how did I get this functor from modules to INTCO? What I did was I said, first, there's a functor from here to here. Namely, I embed, and then I embed. And then by general formal reasons, that extends to a functor out of here. So that's what this universal property of int categories is the functor extends. And you can see that it's fully faithful because it sends compacts to compacts. Does that answer your question? OK. Other questions? So, OK, so this example, let me just highlight for a second, illustrates something which is like very typical of the coherent singular support world, which is that you compare essentially perfect and coherent complexes, or sort of all modules and something that we'll call INTCO. And what you end up with is that, in some sense, perfect complexes correspond to some kind of local nilpotency condition. So that's the thing I want embedded in your brainstem after this example, is that something perfect has something to do with some kind of local nilpotency. Yeah, and I wanted to make a quick remark. Oh no, I shouldn't erase that. So there's a kind of funny remark, which is that there's a kind of alternative path here, which is that if instead you took flat k of epsilon modules, so meaning nothing, sorry, let me say complexes of flat k of epsilon modules, and you quotient out by acyclic ones, wait, I'm saying something crazy. No, I just want flat k of epsilon modules. And you consider this as a DG category. This is equivalent in this example to INTCO. So we could have actually ended up at the same category from a different sort of perspective. So I could have realized, in the very first board that what was too naive was the idea of taking literally k of epsilon modules, and what I should actually do is just take complexes of flat ones, and that would kind of force my result to hold. So maybe I should attach warnings to this that such things can be modified in other examples, but you should be careful about it. Like mod homotopy equivalence of complexes. Not quasi-isomorphism, yeah. No, I'm wrong. You invert quasi-isomorphism. Yeah. Wait. Yeah, mod quasi-isomorphism. Thanks. No. So just like for triangulated categories, there's the homotopy category of complexes, and there's the derived category. If you literally work with complexes, you still have to make sure to mod out by different things. So you still get two DG categories. When I write, on the other hand, the other one is a kind of artifact of working, like the DG category that's around that would be like complexes of A modules or something like that, and the homotopy category of that. It's a kind of, the only way I know how to construct that kind of thing is to see it as a kind of artifact of working with complexes too literally or something like that, as opposed to. Anyway, let's talk about it later. Yes, if you only invert homotopy equivalences, what do you get? And let's talk about it afterwards. I'm getting myself confused, so. But I think what you get is just kind of nonsense. The way, like, if you take complexes of A modules and you invert homotopy equivalences, what you get is kind of nonsense. Other questions? OK, so now I want to give. So I have until literally 5 o'clock, right? OK. So now I want to give another, a generalization of this. So of this example. So I'm going to take y to be smooth over k, f to be a function on y, and I'm going to take x to be, I'm going to write the locus where f is equal to 0. So by this, I mean the fiber product, y times over a1 with 0, where this is a, so this is a talk in the derived algebraic geometry half of the conference and not the birational geometry part. So, so there should be some derived scheme somewhere. So this is a derived scheme if f is not flat. So if you don't like those things, you're welcome to assume f is flat for this discussion. And on the other hand, if you're super into derived schemes, then you can assume f is highly non-flat. So I'm going to write quasi-co of x to mean, again, the DG category of quasi-coherent sheaves. So for these purposes, it's perfectly fine to think x is affine. And now this is just another name for A modules, where A is the corresponding algebra. And I want to say that for f, an object of this quasi-co, there exists a canonical map from f to f with a shift by 2, which I'm going to call eta, which is natural in f. So this is a construction. And this construction plays an important role. So so the claim is that a somewhat better way to say it is the following. Yeah, so I guess, yeah, I'm going to use a bit of notation. So if f from x to y is a map of, let me not get into it too much, but say suitably finite k-schemes, maybe derived k-schemes, then there exist functors. So there's a pullback functor from quasi-co, okay. G is a map from S to T. We don't get too confused. So there's a functor of pullback from quasi-co of T to quasi-co of S. And there's a right, it has a right adjoint which goes the other way. And their adjoint, which I'll just briefly summarize like this. So now in my setup, where I have this particular x, which is the locus where my function f was 0, I claim that the following happens. So if you take f, it's going to, sorry. So take your quasi-coherent sheaf f, push it forward to y, and then pull it back. So here, like this pullback is really a derived functor. This has a canonical map to f, and I claim that the homotopy kernel is just f shifted by 1. So what should I call this map? Lambda. So in other words, I have an exact triangle like this, and then usual, derived category stuff. Gives rise to a boundary map, which now goes from f to f shifted by 2. And this is my map eta. So I think that, so it takes a little bit of care to prove this maybe properly. Let me leave it to people who are interested to ask questions afterward. But it should be very plausible from the perspective of kind of causal complexes. This has the right size. That the size of this is approximately f direct sum f shifted by 1. So the statement is actually that there's a kind of filtration on this object that has these as the two associated graded pieces. So now I get this boundary map. And I want to use this boundary map to give a similar kind of statement to what we said for the dual numbers. So I guess I should say the dual numbers are one example of a schema of this form. The locus in A1 where the function t goes to t squared is 0. So in order to do that, So this is some general thing for schemes, again, suitably of finite type, or DG schemes. So I'm going to say co inside of quasi-co is the full subcategory of bounded complexes with locally finitely generated cohomology groups. So this generalizes the definition we gave for the dual numbers. And now, so if X is a DG scheme with OX bounded below, so that doesn't have to happen. So this is true for us. Then perf of X is contained inside of co of X. So when I say co, I really mean that they're bounded complexes. So for some nasty DG schemes, this isn't going to be the case. But for the examples we consider, it mostly will be. And so we have the same kind of embedding in this case. And that's going to give, again, an embedding of quasi-co of X. It embeds into int co of X. So now again, for sort of formal reasons, this eta extends to int co also. In other words, what I mean is that if I have f in int co of x, for our x, this hypersurface example, there's this natural map from eta from f to f shifted by 2. So again, this follows, if you sort of say the correct infinity categorical words, then this follows just by int extension from co. So I constructed this eta on all of quasi-co of x, and now just for formal reasons, it'll extend to all of int co. So that's what the word natural is doing here. And let me just give a quick proposition. And then we'll be done. So proposition is that quasi-co of x in the setup inside of int co of x is the full subcategory where eta acts locally nilpotently. By which I mean that the colimit of f shifted now by 2n is equal to 0. So it's the subcategory of f's such that this colimit is equal to 0. Yeah. X is the hypersurface, and Y is the ambient smooth thing.
So is eta is just the obstruction to extending f to first order definition?
Yeah. So let me just give the proof. So if you take, so first, okay, so there are two inclusions we're supposed to give here. So we have two subcategories of int co of x, and I want to show that they're the same. So I should show category A is contained in B, and category B is contained in A. So for one thing, so let me show that these objects which, let me show that that eta acts locally nilpotently on all objects of quasi-co of X. Actually, no, the other implication is more interesting. Sorry. So let me show that, that if eta x locally nilpotently, then my object is in quasi-co. So first, there's a claim, which is that that for every f in int_co, the kernel of eta is in quasi-co. And here, the proof of that is that, or sort of the homotopy kernel of eta. So the way I set this up, the homotopy kernel of eta, let me just remind, it was exactly this I upper star, I lower star of f. So first, I'll assume f is in co of x. So this suffices by an argument about closure under co-limits. Now, in this case, the homotopy kernel of eta was just this complex. And this is actually always in perf of x. That's because I star of f is in co of y, which is equal to perf of y by a theorem of Serre. So Serre says that for smooth or regular schemes, coherent complexes are the same as perfect complexes. Now, let me just kind of outline the rest. So an inductive argument is going to show that the homotopy kernel of eta to the n is always in quasi-co of x for every n greater than or equal to 0. Oh, greater than 0. So just a big diagram chase is going to give you this result. And then you pass to the direct limit, and you'll get, so to say, the homotopy kernel of the map eta infinity, which goes from f to this co-limit, is in quasi-co. Yeah?
True that you can just take this co-limit, cut off one door, and get the same co-limit, and put it as a natural triangle.
I think that's what I'm saying.
Yes, but
You
you don't need this.
don't need what? OK, yeah. Maybe I didn't understand the question. So, OK, so what I'm saying is that you can take this kernel of the map from f to this direct limit. But in the case where this is 0, what I'm ending up with is that f is itself actually in quasi-co of x, because this is 0. So f is equal to the kernel of that map. This thing?
No, the homotopy kernel of the map from f to the co-limit.
It's not 0.
It's isomorphic to the same co-limit.
It's isomorphic to the same co-limit. Maybe with a, yeah. No, because eta can act locally nilpotently, in which case this is 0. And then the homotopy kernel is isomorphic to f, not 0. Yeah. So this gives you that the local nilpotency condition implies quasi-co is in int_co. The other direction, let me just say very briefly, follows very similarly the reasoning from the dual numbers case. So if x is affine, you just show that OX has this eta operator acting by 0. So that'll be for similarly stupid reasons. The sequence will just split. And in general, you can do a descent argument to say that any perfect, that'll give you any perfect complex on an affine has this property, and then every object of quasi-co has this property. And a similar descent argument will reduce you to the affine case. So let me omit the details there. But what we ended up with was a generalization of that phenomenon we saw earlier. Local nilpotency sort of corresponds to being quasi-coherent as opposed to int-coherent. So we'll talk more about that phenomenon tomorrow. Yeah. Thank you. So yeah, there are different possible answers to that question. Sorry. So the question was, why? So the question was, what's the motivation? Where does all of this come from? So there are different possible perspectives. So one answer would be kind of from this perspective. So one of the major takeaways from Serre's theorem is that somehow the difference between coherent complexes and perfect complexes has something to do with the singularities of a scheme. And so it may become desirable to understand that essentially as quantitatively as possible in some kind of examples. And so that's one of the things that this coherent singular support does, is it really gives you a large class of examples in which this Serre's theorem becomes somehow much more, quantitative in some sense. Yeah, for hypersurfaces, you don't really get anything interesting because we just saw kind of two classes here. So there was like coherent and perfect. But if you take something which is a more general complete intersection, then you'll end up with some kind of stratification of coherent complexes where you say, well, they're kind of perfect in this direction, but not in that direction, in some sense. So that's one kind of answer. The historical answer or whatever is that there's some motivation out of the geometric Langlands conjecture. So people realized that in some example there was a desire for a category that was bigger than perf but smaller than co, and in this particular example there's a kind of lovely answer in terms of this singular support stuff. Yeah.